Hi, thank you. Good afternoon. My name is Louisa Savereide. I am a first-year graduate student in the Department of Chemical and Biological Engineering. And my research has to do with something you're probably all somewhat familiar with. For example, you're biking home from work and you're stuck behind a bus, and every time it takes off, you are bathed in smoke, and it's very apparent, you can smell it, that the chemicals coming out of the tailpipe are not air. There are a number of chemicals coming out, including things like carbon monoxide, which is poisonous. We have detectors for it in our homes. Nitrogen monoxide, also poisonous. Nitrous oxide, which isn't poisonous. It's more commonly known as laughing gas, but it would still be bad to have too much of it in the air. Not just because it would keep anyone from getting anything done, but it also causes acid rain. It turns into nitric acid, and it's really, really potent in causing global warming by trapping heat in the environment. So back in the 1970s, the EPA decided enough's enough. Somebody has to figure out how to keep these chemicals from getting out of the cars, or else we won't let you make them anymore. Well, I don't know if they said exactly that, but the car companies figured it out. They decided to use a catalyst, something that speeds up a reaction without being broken down in the process, to break down these chemicals, nitrous oxide, that are nitrogen and oxygen stuck together, and when they're still hot and in the tailpipe, break them down to being just regular oxygen and nitrogen, or air. And so platinum works pretty well, except for there are some issues. First of all, immediately apparent is the cost. It's one of the most expensive metals in the world, which makes it expensive for you to buy. It makes it kind of a target for thieves. If you have a saw and nobody's watching, the catalysts in the trucks are here on the outside, and so you can just saw it off and take it home with you. And that's really bad. Also, if you are in a poorer country, it might not be your priority to control emissions because it is just so expensive to have these catalysts in place. One of the reasons it's so expensive is because the production is so challenging. You can only really find platinum in two places, in South Africa and in Russia. So once you found it, you have to take 10 big tons of this stuff out of the ground and process it in order to get a single ounce of the final raw metal. And once you have that stuff, it's not like it's just readily available. You have to process it with grinding and energy and heat and acid. It's environmentally very unfriendly. And on a more technical note, the way that these platinum catalysts work, you need to have an exact balance of air and gas in your engine. So you can imagine that if you have an exact mixture, some of the gas probably won't get quite burned as efficiently as it could be. If you were able to flood the engine with air, then you could have way more efficient burning of gas and improve the mileage of every car in the country. But platinum doesn't work in this way. So since the 1970s, although there have been no commercially available catalysts that have been developed, some progress has been made on figuring out how we can make a better catalyst. And one very interesting possibility is that iron actually shows some of the same catalytic properties as platinum. When you combine iron and sodium and Ceria, which is a white powder that you might have at home already as a glass polishing tool, you get some of the same catalytic results as you get with platinum. And theoretically, you could have something that'd be way cheaper, that would be better at controlling pollution, and that would have more flexible running conditions that would allow you to get that better mileage. So my research has to do with figuring out how these catalysts actually work. So I start by synthesizing materials where I take different types and different amounts of iron and sodium and putting them on the surface, then figuring out what the structure is and how that relates to the way that I synthesized it, and then finally seeing how well the catalysts work and trying to tie everything together so that I can better design the catalyst the next time. So, for example, one of the really cool parts of my job is that I get to make these bright red crystals, like these ones here, and one of the things we hypothesize is that by having these iron clusters that have bigger molecules around them, then when you put them on the surface, they are going to be more spread out and hopefully more effective as catalysts. We also can control what kind of support we actually have. So usually the Ceria is just kind of a randomly shaped powder, but by treating it at high pressures and temperatures, you can force it into specific shapes like rods, octahedra, or cubes, which also gives us more information about how the catalysts work. Finally, I get to test them all in a reactor that I'm building right now that's just like a car tailpipe, except way more expensive, because you can measure exactly and control what's going in, and you can measure what's coming out and compare in very precise conditions how these catalysts are working. So to summarize, and in conclusion, iron has a very real possibility of replacing all of the platinum in our cars. And this would be great because it would be way cheaper, both when you're buying the catalyst and when you're buying gas. It would improve the environment because everyone would have access to these catalysts that are so crucially important for saving the environment, and it would maybe even work better than platinum. And finally, in the process, we would have developed a better understanding of the really interesting chemistry behind how these catalysts work. Thank you very much.